Okay, so let's begin our first lecture um, on some of the observations that we need to ultimately explain. So we're looking at an image from the James Webb Space Telescope, and we're seeing a very small portion of the sky. I'm actually not sure about this, but I would imagine that all of this whole area here has a sort of a radius of just a few millimeters. And you collect the light in that small area, and this is what you see, a collection of many galaxies. And some strange effects like this, for example, these are stars getting in the way. These are diffraction patterns from things that are not very far away. So we see all of these different galaxies. So here it looks a little bit like a somewhat flatter galaxy. Then there are things like this, which are more oval, elliptical galaxies, sort of puffed up structures. Here's another spiral galaxy. We're looking at it face on. And our current cosmological picture is that these galaxies on very large scales are ultimately moving away from each other. On small scales, there's all sorts of different kinds of dynamics, but on the largest scales, we see that structures are receding from each other, and we call this the expansion of the universe. And what we've learned over the last, maybe we could say 100 years or so, is that in every galaxy that we've been able to make the measurements, there is a very massive black hole at the center of the galaxy. And this black hole is instrumental in the way the galaxy forms, perhaps evolves, and we'll discuss the correlations that we found and ultimately want to explain them because these are correlations between black holes and their galaxies, and they are, in some sense, rather surprising. So I think it's fair to say that most galaxies seem to be, in some sense, normal in that most of this light is coming from stars. There's gas and there's dust and there's planets. But in about 10% of galaxies, as we've observed so far, there's something special going on. There's some large amount of energy that's coming from the centers of these galaxies. And so these galaxies are called active galaxies. And so 10% of galaxies are active. And after many decades exploring this idea, which sort of began in the 1950s, we kind of converged on a paradigm for active galaxies, which is that at the very center of the galaxies, now this is a cartoon, at the very center of a galaxy or of an active galaxy, there is gas that is funneled into the center, and that gas has to sort of flatten out. It's being pulled into the center, but it has to obey energy and angular momentum conservation principles, and so it sort of flattens out into a disk. And so here there would be a black hole. The closer you get, the flatter you get in this cartoon, and this somehow produces also this white jet of energy that's coming out. We'll talk about this in more detail later on. But this kind of seemingly exotic object is actually very common because these are just basic principles. As I mentioned here, planets, stars, and galaxies seem to form this way. If we think of the solar system, we see the sun at the center, and then the planets are all rotating in a plane. And that plane is ultimately thought to be the relic of all the stuff that fell into the center, formed the sun. The accretion disk is called, and planets accumulated matter, and it got bigger, but they all share the same plane. We see galaxies that are flat, the spiral galaxies, and we think it's just the same principle, energy and angular momentum, over time flatten these structures out. So let's talk a little bit about these jets. Now, not all active galaxies have jets, so really this is an important thing to point out and that we ultimately need to explain. So we'll see that about 20% of active galaxies have jets, and so jets are a minority among the active galaxies, and the active galaxies are active in some other sense, which we'll discuss, which has to do with this disk of stuff falling in and shining brightly. So here is what's called, here is an FR1 jet. This is an actual image. These things are often seen in radio, so these are low frequency. We have a good sense of what's causing them because we understand the signatures. It's synchrotron radiation, electrons, and magnetic fields. So here is sort of the center of this galaxy, and a jet is coming out this way and that way, so sort of left and up and right and down. And we think the black hole is at the center there. And this kind of jet quickly interacts with the medium, with the interstellar medium, and in some cases the intergalactic medium, and loses its energy, and it starts to sort of fizzle out. We see that sort of happening here. And this differentiates itself from jets that are called FR2. So these are classifications associated with people in the 1970s. Fanaroff and Riley classified these. These are sort of the most powerful jets. And an FR2 jet is one where, if this is the center, I think this is the center of the galaxy, we see less interaction with the interstellar medium and intergalactic medium in some of these objects. And the energy gets funneled in this jet in such a way that it manages to get far away before it then ultimately splashes into and interacts with some medium out here. And we call these things hotspots. And so generally, these kinds of jets seem to be more powerful. They tend to be more collimated. Let's go back and look at the FR1 jets. These are less collimated. So maybe it's a combination of the engine, what's going on there, and of the density of the medium to produce what we observe and how these things are distributed in time. And we'll address these kinds of details. So there are a lot more observations to discuss. We're just discussing active galaxies and jets. And so 10% of galaxies are active. 20% of these active galaxies have jets. There are FR2 jets and FR1 jets. And it so happens that FR2 jets are found at higher redshift. And that's something that higher average redshift compared to FR1 jets. So we need to explain this. Why is that? And then more recently, in the last 5, 6, 7 years or so, we found that there are other kinds of jets, FRO jets have been labeled, and they tend to be more compact, and it's unclear whether these are young jets that will become FR2s or FR1s, and we'll discuss this, and they tend to be in environments that are less dense. We'll discuss all this and try to put them together into a theoretical framework.